Imagine being in this theater on a hot summer day without air conditioning. Pretty uncomfortable, right? What you might not know is that the very technology keeping us cool is now warming the planet. Air conditioning relies on fluids called refrigerants. Most refrigerants we use today are hydrofluorocarbons, which are extremely potent greenhouse gases. As you use them, they leak into the atmosphere, trapping heat, releasing back to Earth. So now, we're stuck in a vicious cycle. To adapt to the rapidly changing climate, we need air conditioning. But as we use more and more ACs, the planet keeps getting warmer. This is a big problem. But maybe not a big problem for a first-year graduate student in chemistry. When I first arrived at Harvard, I never thought I'd be working on anything related to climate change. I was drawn to fundamental science questions. I just wanted to tinker with molecules and understand why they do what they do. And I started with the material known as two-dimensional perovskite. Why? Well, we chemists, we're visual creatures. We love pretty structures. So along with my advisor, Professor Jared Mason, I was drawn to this material simply because it looks interesting. Two-dimensional perovskite features inorganic sheets that are formed by corner-sharing metal halide. They serve as a template to host the long organic chains. These organic chains pack into a bilayer structure. What caught our attention was these organic bilayers can do something very strange. They're dynamic. They can switch between order and disorder. When you increase temperature, this long fluffy chain starts vibrating, wiggling, and twisting. And at around room temperature, they undergo a sharp phase transition. They expand, storing a high density of thermal energy. What is fascinating is that these chains are so disordered, they resemble molecules in a liquid. In other words, this is a solid that behaves like a liquid. You can always transform these chains back to order by simply lowering temperature. When you lower the temperature, chains become frozen, releasing heat. The bilayers contract. I was fascinated by this phenomena, and I began to synthesize a wide range of compounds featuring these organic bilayers, and I studied their phase transitions. I was using these materials as a playground to explore the relationship between molecular structures and thermal energy. Like I said, we chemists, we love to tinker with interesting structures. At the same time, this fundamental investigation got me thinking about what I could do with these unusual solids. So first, I started imagining different ways to control this transition. For example, I thought instead of using temperature, we should be able to use pressure to control their state because these bilayers are squishy. When you compress this material, they contract. They contract, and by contracting, they release heat. You can also reverse it back by removing pressure. When you remove pressure, they slowly expand, absorbing heat. So I was thinking about this idea. While doing so, I started reading papers outside chemistry. I came across a group of people, philosophers, engineers, and physicists, who have been studying heat in solid. And some of them have been trying to use solids for cooling. For example, squeezing certain materials can trigger phase transition and temperature change, which can be used to move heat. But the problem is, this process is often not reversible unless you apply extremely large pressure. Okay, so I found these papers interesting, but nothing really happened for weeks. But then, it hit me. I realized the material that I've been studying all along, this strange solid that behaves like a liquid, might be an ideal refrigerant for cooling. These organic bilayers are compressible, and their transitions involve substantial changes in energy and volume. The combination of this property should allow them to absorb, release a large amount of heat, at low pressure. And this reversible process, when combined with the proper heat transfer system, can be used to move heat from inside to outside, providing cooling. So after I made this conceptual leap, I spent the past 4 years establishing this material as new class of solid refrigerant. To study how they respond to pressure, I spent many hours in the lab performing a series of high-pressure experiments. In doing so, I was able to understand and improve their cooling performance. In one of these experiments, I measured the sensitivity of phase transition to pressure to get the diagram, so-called a phase diagram. And using this diagram, we could also perform an experiment to directly measure the flow of heat that goes in and out of the material as we change pressure. And using this experiment, we're able to demonstrate these organic bilayers indeed provide a powerful mechanism for cooling. So now we're convinced that these solid refrigerants open many exciting possibilities. By replacing these harmful gas refrigerants, we can finally break the feedback loop between cooling and climate change. We can also go beyond the climate impact. We can start reinventing air conditioning. We can develop cooling devices that are efficient and compact. And more excitingly, we can even bring this invention to the places where conventional cooling technology don't work really well, like in outer space. Now, we are working with engineers to build a prototype cooling device. We're going to bring this discovery to life. So this is a story of how a chemist ended up working on air conditioning. I never thought tinkering with molecule in the lab will lead to a possible solution to climate change. But I think that's the beauty of fundamental research. It's not always clear where my exploration will lead me. But when the right connections are made, it can lead to unexpected turns with unexpected discovery. So what's next? I don't know. What I do know is I'm excited to continue my journey as a chemist, hunting for the next discovery. Thank you.